In Chapter 5, we switch from discrete random variables to continuous random variables. So before we jump into the first slide, remember that discrete data is data that's typically gathered through counts, right? We're counting something, and continuous data is usually coming from things that are measured. So that means that for discrete data, there are only certain values that are permitted, but with continuous data, basically anything may be possible. So our objectives for Chapter 5 are just to recognize and understand when a continuous probability density function is and when it should be used, recognize the uniform distribution and the exponential distribution. Some properties of continuous random variables. Instead of dealing with tables like we did for discrete data, we're going to deal with graphs, okay? And the graph of a continuous probability distribution is a curve, okay? Sometimes a straight line, but generally speaking, it's a function with a curve. The probability that we're going to be dealing with now is represented by the area under that curve, okay? The area between the curve and the x-axis. And you may think that I'm repeating myself as we go through this chapter because that point is important, and I'm going to bring it up multiple times. That the probability is the area under the curve. The curve itself, we call it the probability density function, a little different than discrete. We called it the probability distribution function. So when we're dealing with continuous, we use the word density. Again, that's because of that whole concept of probability is area. We usually refer to the PDF as f of x. That's kind of just the name we give it generally. And quite often we can find a second function that that models the area under the curve. Okay, so instead of the function that gives us the curve itself, this would be a function that gives us the area under the curve. We call that the cumulative distribution function, or CDF. The total area under a PDF curve is always equal to 1. Okay, just like in the discrete chapter where we had tables and the probability all had to add up to 1. Same concept. Okay, because area and probability are now equal, they're the same thing. Now the area must be 1 in order for the PDF to be legitimate. In this chapter, we're only going to be able to find probability for intervals. We're not going to be able to find the probability for individual values. Again, because we're dealing with area, there has to be some space in there that we're trying to find the probability of. So if you try to find the probability of a straight line, or I should say the area of a straight line, this is going to make more sense once you see some graphs, but if I just said, what's the probability that x equals 3? Well, x equals 3 is a vertical line, right? Remember from algebra? So basically what you're asking for is the area of a straight line, which is 0. So we can't find probabilities for individual values. Instead, we find probabilities for intervals. So like from x between 3 and 5, for example. All right, so that last point is again just saying that the probability that x is between two values is the area under the curve and above the x-axis between those two values. There are 3 continuous distributions in this chapter that I shouldn't say in this chapter. There are 2 in this chapter, and then chapter 6 is entirely dedicated to the third. Okay, the third distribution is the most important one. But the first one that we'll deal with in this chapter is the uniform distribution. And the uniform distribution is where every outcome is equally likely, and so what we have is a straight line that represents our PDF function. So finding the area of these, finding probability, comes down to finding area of a rectangle. Okay, so it's very easy as long as you remember that probability is equal to area. Our second distribution function is the exponential distribution function. So finding the area on this one is not as easy as finding the area of a rectangle, but fortunately we have some formulas that we can use to find areas in cooperation with our calculator. We'll be able to find these. So notice that on the first picture there, the uniform distribution, That shaded region represents the probability that x is between 3 and 6. And on the second picture, the exponential distribution that represents the shaded region represents the probability that x is between 2 and 4. The third distribution, and again, this is the one that's in chapter 6, is the normal distribution. Okay, this is the bell curve. If you've ever heard the term bell curve, this is what that's referring to. I think we talked a little bit maybe about bell curves when we looked at histograms in chapter 2. But honestly, it blurs a little. I can't remember. So the normal distribution is very, very important. Okay, it shows up in unexpected places. So this one, the shaded region here, represents the probability that x is between 1 and 2 on a normal curve. Section 1, now actually jumping into the meat of the chapter itself, is just talking about continuous probability functions in general. So it just allows us to kind of get our feet wet. And again, here I am repeating myself. Probability is area. Okay. We know a lot about functions from our work with algebra. So CDF functions are special in that we plug a couple of x values into them and we can find an area underneath our PDF curve. All right, so again, keep in mind that the total area underneath that curve is always going to be 1. And so let's look at this one here. Okay, we'll consider the function that f of x is 1 over 20 between 0 and 20. Okay, we can confirm that this is a proper PDF function because if we take the height of this rectangle, which is 1/20th, and we multiply it by the width of this rectangle, which is 20, 1/20th times 20 gives us 1. So the area inside this rectangle is 1, which makes it legitimate, so to speak, as a PDF function. All right, section 2 is, I know that seemed quick, but section 2 is the uniform distribution. This is where we get to do a little more math, a little more stuff. So the uniform distribution is just like the one I just showed you. It's all the events are equally likely, so our curve is a horizontal line. A couple of important statistics about the distribution is that you can find the mean by taking A, which is the left end of the domain, plus B, which is the right end of the domain, and dividing by 2. So basically the average of the endpoints. Standard deviation is a little more complicated, but still not bad. You subtract B minus A, square that, divide it by 12, and then take the square root. All right, that would be your standard deviation. When referring to the uniform distribution, we say that x is distributed as uniform, okay, capital U, from A to B. All right, all we need are the left and right endpoints. So basically, A is the lowest possible value for x, and B is the highest possible value for x. Okay, so that's our notation there for uniform. And here is example 5.2. So we'll switch over to our document camera to do example 5.2 because that way we can draw the distribution curve and work out these problems. In example 5.2, the explanation in the textbook provides a little more detail on this, but basically it boils down to they got 8-week-old babies to smile, and they measured they timed how long the baby smiled. So it turned out that the baby smiles were uniformly distributed between 0 and 23 seconds. So it seems a little odd, but I don't know, whatever. So the mean and the standard deviation here. First of all, the mean is 0 plus 23 divided by 2. So that is, 11.5? So 11.5 seconds. The original data was in seconds, so our mean is also in seconds. The standard deviation, a little more complicated formula, 23 minus 0 squared divided by 12, and then we take the square root of that. So 23 over 12 is slightly less than 2. I'm going to have to get my calculator to do the square root anyway, so I might as well do it now. Let's see, 23 over 12 is 1.916. Oh wait, no, my mistake. 23 squared divided by 12. Almost messed up. 44. Let me take the square root of that. 6.64. All right, so we'll say 6.6 seconds. All right. Glad I caught that square issue before it was actually a mistake. So that's part A of example 5.2. Find the mean and the standard deviation. Now, we don't really need to draw the graph to do these first two steps, but the next part's asking us for a probability. Specifically, what is the probability that a randomly selected baby smiles for between 5 and 10 seconds? So that would be the probability that x is greater than 5 and less than 10. So now I think it's worth sketching the PDF graph, which fortunately is pretty easy because PDF graphs are all rectangles. So here's the y-axis, here's the x-axis. We know that this goes from 0 to 23, which means that if the base is 23 units long, then this height must be 1/23rd, right? So there's our f of x function, because 23 times 1/23rd would give us an area of 1 inside this rectangle. But we know that the whole area is 1. That's not the issue. What we really want to find is what's the probability that x is between 5 and 10. Okay, so we want to know that area in there. So since our rectangle is 1/23rd units tall, and now we know that this area we're interested in is 5 units wide, then our probability is 5/23, or 0.217. So our probability that x is between 5 and 10 is about 0.217. Okay, part C is asking us for the 90th percentile. Okay, and we haven't talked about percentiles in a little while, but hopefully it hasn't been so long that you don't recall. Basically, the idea is we want to know what, okay, just redrawing this picture. We want to know what is the x value that would give us 90% in there, or in other words, an area of 0.90 inside this rectangle. Okay, so we don't know exactly what the number is where it'll stop, but we know that we'd had 90% in here, 10% in there, and so our goal is to find x. So again, since we know that the height of this rectangle is 1/23rd, basically what we're trying to say is we're going to take 1/23rd and we're going to multiply it by some x value, and that's going to give us 0.90. So solving for x, we'd multiply both sides by 23. We get 0.9 times 23 gives us an x of 20.7. All right, so our 90th percentile value is 20.7. And the nice thing about dealing with continuous probability distributions is we don't have to try to round it to the nearest value that shows up in the data or anything like that. This is fine, right? 20.7 is a perfectly reasonable number if you're dealing with continuous data. So that's our 90th percentile value, and that wraps up example 5.2. All right, for suggested homework on section 2, this is just basically one set of problems off of one distribution. So 16 through 25 is all referring to the same distribution. So if that doesn't feel like quite enough, the one right below it, I think it's 26 to 33. That may be additional practice that you might want to look at, just in case the 16 to 25 isn't quite enough. So let me know if you have any questions on this, and thank you very much.